Example number 2. We want to find the limit as x approaches to positive infinity and negative infinity of the function 1 over x. If you recall from recalculus, the function 1 over x look like this. So now we look at the x approach to positive infinity. So go like this way. So what happens is if you keep extend that side, it just keep closer to the 0 for the y, and the x just get larger. So for example, just look at this point in the very far away. The x is really large and the y is close to 0. You notice that it's never be 0, okay? So we would say that the limit of 1 over x as x approach to positive infinity is 0. And similarly, we go from the other side and we can see that it's also 0 as x approach to negative infinity. So theorem number 5 said that if r is a rational number, then we have the limit of 1 over x to the r when x approach to positive or negative infinity equal to 0. So the proof is pretty easy. So we see that we have the limit of 1 over x to the r. Oh, by the way, the rational number is like 2 over 3, like negative 4 over 7, or 5, and it's like 5 over 1. So they are all rational number. So we have 1 over x to the r. So in algebra, this is mean 1 over x, the whole thing to the power r. And from this step, we are using theorem number 8 in section 2.5, the section before. So we can pull out the function outside, and from the example number 2, this is 0 to the power r and is equal to 0. And similarly, when x approaches to negative infinity, we have the inside approach to 0 by example number 2 we just did, to the r power and is equal to 0. So let's do some application for this theorem. So example number 3. When you look at example number 3, you think that we may need to log in the infinity at the x location right here, right? But what happened is that let's think about x is like 1 million. On the top, you get very large number. And in the bottom, you get really large number. So you know that there are very large number, but you don't know exactly what is that number. So maybe this is like 1 million divided by 0.5 million, for example. Yes, we don't know about it. They are both very big. So we're not going to plug in the infinity right away, but we need to fix. We're using some algebra to fix this. And what we just learned is about 1 over x and 1 over x to the power r. When the limit go to infinity, x go to infinity, both of them will become 0. So I'm going to use that for this problem, okay? So we know that the limit of x go to infinity of 3x squared minus x minus 2. So what I'm going to do is I'm going to divide the top and bottom by the same number. So let's copy this down first. You know, if I divide top and bottom by the same number, x squared, the way to do is you're going to look at the biggest exponent, okay? So this is the same thing because I divide by x squared and x squared. For top and bottom, I will keep the same expression. Okay, so another way to write like this is like this. So then limit as x approaches to infinity. So what do we got is 3 minus 1 over x minus 2x squared. And then 5 plus 4 over x minus 1 over x squared. This is the quotient, so it can be the limit of the top and the limit of the bottom. So we can separate them. And also between them is the plus and the minus. So we can use law number 1, the limit law number 1, it will be the limit of 1 by 1. You do the same thing for the bottom. You're going to separate them, okay? So what do we know about this one and this one, this one and this one? So we just learned in theorem 5 and the example number 2 above, the limit as x approaches to infinity of 1 over x or 1 over x to the power r will approach to 0. So 3 and 5 on the top and the bottom, they are both constant. So it's equal to 3 over 5 minus 0 minus 0 plus 0 minus 0. So the final answer is 3 over 5.